Question 1, is that at all readable if I put it this size? And I can do it bigger, but then I'll have to scroll. Is it better like this? Okay. Question 1, parts A through C, like I said, pretty much the only things that people did wrong on that one is either they misread the question and took the intersection of the wrong thing, or they did not realize that 2 is prime and 1 is not. And yeah, neither of those mistakes was penalized particularly harshly because I'm not that worried about it. And in terms of tips for gaming the exam, like, at least when I write qualifying exam questions, this isn't universally true of my colleagues, but I remember when I took these exams myself and couldn't sleep the night before and went in there with my hands shaking because I thought I wasn't going to know how to answer anything and fail and stuff. So I like to put a softball question towards the beginning of the exam. So just as kind of a confidence builder, like, okay, I know at least one thing, maybe I won't totally fail. So if you find my question, it will probably have a softball in it, just FYI. Part D, on the other hand, that was one of the more common mistakes on the exam. I think very few people got this one. And I mean, a lot of it just seemed to be some confusion about the definition of a sigma field. If you're an MS student, you may not need to worry about it that much. This, to me, is just something you should be aware that they exist, but I don't think it's something that routinely gets tested on qualifying exams or things like that. But if you're planning on taking 760, you need to know this. I mean, first of all, keep in mind that a sigma field is always going to be a set of subsets of some larger set, usually denoted by omega. So in this case, omega was the set of natural numbers. So I mean, a number of people just said, okay, well, the set of numbers 1 to 5 is the sigma field. Well, no, it has to be a set of subsets of the natural numbers. And another thing, all sigma fields will always contain omega, and they'll always contain the empty set. In fact, it's fairly easy to prove that the condition that a sigma field has to be non-empty is equivalent to the condition that it contains the empty set. I mean, a simple example, I'll put chalk down on the other end. I guess this piece is probably good enough. If a sigma field's non-empty, it contains some x. Since it's closed under complements, that means that x complement also has to be contained in F. And since it's closed under finite unions, x union x complement, which is equal to omega, has to be contained in F. So that implies that omega complement, which is the empty set, also has to be contained in F. And for this particular problem, that basically gives you the smallest sigma field right there, that the sigma field generated by A, obviously it has to contain A at the bare minimum. Since it's closed under complements, it has to contain A complement. And so you add in that has to contain A union A complement, which is of course the set of all natural numbers, and it has to contain the empty set. So now we have a set with these 4 elements here. Empty set, A complement, and the natural numbers. Is that closed under complements? Yes. Is it closed under countable, or in this case just finite unions, there's only a finite number of things? Yes. Is it a sigma field? Yes. We're done. That's anything smaller would not be a sigma field because the argument I just outlined, it has to contain at least those 4 things. So, all that makes sense to everyone? Okay, on to question 2. Most everyone got parts A and B. Those are both just fairly standard probability calculations. If you didn't get it, you can take a look at the solutions, but most people did, and when people didn't get them most of the time, it was just like a careless mistake where they wrote the wrong probabilities at some step, and I didn't penalize heavily for that. Part C confused a lot of people, and that was a more convoluted problem that, in terms of the setup, that, I mean, it's, as I read through it, a lot of people just did not know how to deal with this part, that you take 10 transistors from the box and only one was defective, that they wanted to say, okay, that means that it must have been box 2. Well, it's more complicated than that. So, how did I define my notation here? I said E is the event that 1 turns up, F is an odd number other than 1, and G is an even number. So, we're given that it's not G, but that means that the die could have turned up 1, or it could have turned up some number other than 1. The probability of getting 1 defective in 10 tries given E or given F is just a binomial probability with those two probabilities there. So in this case, we want to find the probability that the die landed 1 given that, given S, the 1 defective in 10 tries, and that it's not even. So then using the formulas for this type of probability and eventually Bayes' rule and so forth, want to find the probability that it's the die is 1 and 1 defective in 10 tries and not even, the probability of 1 defective in 10 tries and that it's not even. So at the top, obviously if it's 1, then it's not even, so the top is just going to be the probability of 1 defective in 10 tries, and the die is 1. The bottom, you can break up into 2 disjoint pieces, the probability of 1 defective in 10 tries, and it's 1, plus the probability it's 1 defective in 10 tries, and it's some odd number other than 1. And then you can rewrite that in conditional probabilities. Each of those pieces we've calculated previously turns out to be about 2.289. That makes sense. Go on to problem 3. Problem 3 was kind of mixed. A lot of people got it, a lot of people didn't. And I mean, I think a lot of it just boiled down to, did you recognize this as an occupancy problem? If you did, then you got it. I mean, part A, a number of people just enumerated all the different possibilities, even if they didn't recognize it as an occupancy problem. That was kind of by design, that even if you didn't recognize it as such, hopefully you can write it all out. Part B, it was basically, if you saw there was an occupancy problem, it was easy. Otherwise, it was at best painful, and at worst, you probably got it wrong. I mean, one comment that I was going to make here is like the whole reason why I did this whole business with partial derivatives was just the like trying to force you to think outside the proverbial box a bit and have to see, oh wait, this is a situation where you would use the occupancy problem. I mean, a number of people just either wrote explicitly on the page, I don't remember how partial derivatives work, or just based on what they wrote, obviously did not remember the fact that like you can just differentiate, you can take like a partial derivative, something like, as you would say, where you just differentiate with respect to the same variable twice. A lot of people didn't count that, and I try not to penalize too heavily for it, but for stuff like this, I mean, if you can't remember how this works, I mean, this is designed to be a test. Can you recognize this as an occupancy problem? Not, can you remember how to do partial derivatives from calculus a number of years ago? If you can't remember those details, you are welcome to ask. I can't promise that I will tell you, but if it's something that I do think you should know, but you're welcome to ask, and I would recommend that you ask rather than just like not answer the question or get the wrong answer. Question 3, any more questions on that? Question 4, generally, people did pretty well on this one. It was fairly standard combinatorics. If you had any questions, feel free to read through the solutions, but it's basically when samplings with replacement, there's 5 choose 2 possible orderings. If the second white ball's in position K, there's K minus 1 possibilities for the first white ball. Or, I mean, you can just enumerate the possibilities, which a number of people did. CDF, pretty much everyone got. Part C was the one where people had more trouble. Still, I would say most people did fairly well on this. But, I mean, one common mistake was that since the sampling is with replacement here, in theory, it could take more than 5 tries. A lot of people only calculated the probabilities up to 5 and said that they were done. It wasn't something I penalized heavily for if you got the rest right, but otherwise, I mean, this is just basically what it reduces to negative binomial distribution. What's the probability that it takes K trials to get 2 successes? Any questions on number 4? Number 5, part A, most people did reasonably well. At least most people got the x over 2 part okay. The biggest potential mistake people would make here is that in order for it to be a CDF, the probability has to go to 0 at -1, has to go to 1 at 1. So you take the antiderivative of 1/2, you get x over 2 plus c. You need to figure out that c is equal to 1/2. Most people did, but there were a significant number that missed that piece. And part B turned out to be kind of tricky on a number of levels. I guess maybe I just didn't give enough practice with this in the homework, or this was a little bit different than the way it worked in the homework. But a decent number of you did figure out that the CDF between 0 and 1 is 1/2 plus y over 2, but almost no one recognized the fact that for the interval between, if x is between -1 and 0, then y will be exactly equal to 0, and there's a probability 1/2 of that happening, since the probability of getting between -1 and 0 on a uniform -1 to 1 distribution is 1/2. So the probability distribution for y here, or the CDF specifically, is obviously there's a 0 probability of getting less than 0, but there's a probability of 1/2 that y is exactly equal to 0, which corresponds to x being between -1 and 0, and then if x ends up between 0 and 1, the probability of that happening is 1/2 plus y over 2, and then 1 for y greater than 1. So that makes sense where this came from. The PDF, that was kind of, I messed this one up, to be completely honest here, that, like, when I wrote this problem, it did not occur to me that the CDF is not differentiable, so the PDF doesn't actually exist. And that's not something that I had ever inflicted on you in the homework or anything, so it was kind of unfair to ask you to know it. So, generally speaking, if you got the CDF right but messed up the PDF, I did not take off a whole lot of points for that. And there was actually one person who was smart enough to realize that the CDF was not differentiable and wrote approximately what I had for the solution using delta functions, which I probably should have given bonus points for that, because that was definitely beyond anything that I had taught. Was there a question about this? Okay. So on to question 6. This is the formal mathematical solution for it. This question was far and away the least popular of the optional questions. I think there was one person who attempted it seriously, and a second person who just wrote down a couple things. They were clearly running out of time and just wanted to write something for one question. And when I work through this problem, you're probably going to say, like, oh, why didn't I see that sooner? But I think just all the set theory stuff scared people. And when you're taking a time pressure exam, you don't want to sit here and think about what all this weird set theory stuff means. But let's write this out. That we have UK, what is it exactly? Union of AI1 intersect AI2 intersect AIK. And what did I call the other one? IK. It's the intersection of the unions of these things. And we want to show that so what's this statement in set theory language actually mean? That, so we have a bunch of events, A1, A2, up to AN, or just sets generally. And this is basically some arbitrary, what this is saying is you take any k of these n events and take the intersection of them and then union over that for all possible subsets of all possible subsets of size k. That gives you UK. And IK, you take union, more to the point, I of n minus k plus 1 is you take the union of any possible subset of size n minus k plus 1, then take the intersection of all of those. So what does that mean in ordinary English? Well, for UK, what this tells you is that in order to be in this union, you have to be in at least one of these. And to be in at least one of these, that means there has to be some I1, I2, up to IK, such that, maybe I should say for X to be in UK, that implies there has to be at least one AI1, AI2, up to AIK, such that you're in all of them. So in other words, for any given element X, there has to be KAI such that you are in all of them. Does that make sense? And IK, conversely, since it's the intersection of the unions, to be in this union, you have to be in one of these. And to be in the intersection, that means you have to be in all of these. So given, that means take any subset of size n minus k plus 1, and you have to be in at least one of them. Because the intersection implies you have to be in all of these, and in order to be in a given one of these sets, then you have to be in at least one of the constituent sets. So in other words, if you take, there is some subset, to be in UK, that what that says is there is some subset of A's of size k such that you are in all of them. And if you're in IK, what that says is that given any subset of size n minus k plus 1, then you're in at least one of them. So how do you show that they're equal? Well, the usual trick about showing that they're subsets of each other. Let's say that you're in UK for starters. Well, that implies that there's some subset of size k such that you're in all of them. Well, if there's some subset of size k such that you're in all of them, that implies that you're in at least, that any possible subset of size n minus k plus 1 must contain one of these k's, one of these that it's contained in. So any subset of size n minus k plus 1 has to contain at least one of these AIs, so that implies you're in I of k as well. And on the flip side, if you're in I of k, that says if you take any subset of size n minus k plus 1, you have to be contained in at least one of these. So we'll just call that, like, say you're contained in I1, for example. Well, let's take out AI1 and then throw in a new one and repeat this process. Once again, since this has to be true for any possible subset, then there has to be one of these that contains X again. So we'll say that it's AI2. Well, remove AI2 from this sequence, repeat the process. Now you're contained in AI3, for example. Bottom line, you repeat that step k times, you end up with k AIs such that X has to be in every single one of these. Well, that implies that there's a subset of size k of the AIs such that you have to be contained in all of them. So that implies that you're in UK, they're subsets of one another, and hence they're equal. That make any sense at all? Well, there's solutions online. Maybe that problem was too hard and I'm understanding why everyone skipped it. Well, I can use that as a homework problem to torture students next year, I guess. It's probably too hard for an exam problem.
Let us know which one you put that on so we can know when they're really sad.
Okay. So question 7 was not as unpopular as question 6, but it got skipped by a high number of people as well. That the object here was to either prove that something was a field or find a counterexample to show that it's not a field. So for part A, it was that for both of these, I gave you that the universe omega was a subset of F. And basically part A, say something is closed under differences. Does that imply that it's a field? Well, so to show that it's a field, we have to show that oh, and that was a typo on these solutions that I was going to fix, but didn't. Oh well. I'll try to fix it on the solutions on Sakai. But so to show that it's a field, we have to show that it's closed under complements and under finite unions. So first step, let's try to show that the one in part A is closed under complements. So we're given omega is an element of F. Now, say we have A an element of F, want to show A complement's an element of F. Well, we know that it's closed under differences, so in particular, we're given that omega intersects omega, I should say, omega minus A, which by definition is equal to A complement, is an element of F since it's closed under differences, and omega and A are both contained in F. So that gives us that A complement's an element of F, so we're closed under complements. Woohoo. So now we need to show that it's closed under finite unions. So, well, there's a lot of typos in this solution. I'll try to fix this when I get back to my office. So, say we're given A and B contained in F, and we've already shown that it's closed under complements. So that gives us A complement is contained in F, and therefore A complement minus B, which of course is just equal to A complement intersect B complement, is an element of F. But once again, this thing's closed under complement, so the complement A complement intersect B complement complement, which is of course just A union B, is an element of F, so it's closed under unions of two sets, and then it's a fairly easy induction argument to show that if A union B is an element of F, then any set of finite unions is also an element of F. Does that make sense for part A? And part B, well, hopefully you can see the counterexample on the board. What I've written on the board is closed under complements and finite disjoint unions, but you can, if you intersect 1, 2, and 1, 3, that gives you something that's not an element of F, so just because something's closed under the formation of complements and finite disjoint unions, it's not necessarily a field. And yeah, there were only a couple people who got that particular counterexample. I mean, the most common mistake on this one was that people tried to say, well, do the same trick that you did in the homework, where you say, well, given A1, A2, etc., let do the trick where like B1 equals A1, B2 equals A2 minus A1, or etc., etc. The problem with that approach is that there is no guarantee that the way you've set up these B's are going to be elements of F. That there's nothing given there that implies that these differences will necessarily be contained in F, so that particular proof does not work. Any questions on part B? So question 8 was one of the more popular questions, and most people who did it did reasonably well on it. It's essentially, as I said, two negative binomials summed together, and I mean, it's the World Series example that I worked in class last week is basically exactly the same as this. That it's just, if you say I'm going to assume that it's the right bag that was empty, then it just becomes a negative binomial, and likewise, that'd be for the right or the left, I don't know, but one way or another, then you fix the left bag being empty, it's another negative binomial. Since they're disjoint, the total probabilities, you just add the two together. Oh, question 8, straightforward enough. Any questions about this? Well, question 9 was probably the single most popular question on the exam, which, ironically, it was probably the one that people made the most mistakes on as well. That, I guess part B was similar to a homework problem, and this one at least, you could write some stuff on the page and know a way to play around with it, whereas, like, I guess question 6, if you didn't see the trick that I described earlier, you just stare at the page like I have no idea how to do this. But one way or another, like, I mean, I don't know. A lot of it just boils down to doing the right manipulations so that the proof falls out. That, I mean, if you want me to step you through this, I can, but I mean, it's mostly just manipulating probability identities, and you can probably just see this yourself. And like I said, part B was identical to a homework question, so most people did reasonably well on that. The part C and D, I probably threw you for a loop a little bit there. I mean, there were a decent number of people who made it this far on part C, where you said the probability of A and B union C, that could be written as probability of A and B union A and C, and then using the independence of A and B and C, that you can write it like this so that you get the probability of A and B and C equals the probability of A times the probability of B and C. And there were a number of you who said, okay, so by the result of part D, that means that A and B union C are independent. And unfortunately, like I said, I mess with you a little bit in that D is actually false. So when you write these types of proofs, unless you're 100% sure that the other part that I'm asking you to prove is in fact true, you don't want to say that assumption. Had you just said, so if part D is true, then this is true, otherwise it's false, you would have gotten the points, but a lot of people just assume D was true without actually checking on this. And as you can see, D is false because there's a counterexample that, and I mean, I won't go through the details of the counterexample because I think it's reasonably straightforward, but yeah, D is false, and if you do a similar counterexample, it will blow up C as well. Oh, any questions on number 9? Well, question 10 was, along with question 9, also the most popular question on the exam. I think it was another one that easy to play around with and write stuff, but hard to get all the details. And I think there were only a couple people that got it completely right, although there were several that came close. The converse is false, and most people got that. I mean, like, two disjoint events is an obvious counterexample, or you can do something like, I just said flip 2 coins, then A union B is 3 out of 4, A intersect B is 1 out of 4. But in terms of proving that probability of A union B equals probability of A intersect B, that implies probability of A equals probability B. The high percentage of you made it at least this far up here, that 2 times the probability of A and B equals the probability of A plus the probability of B. From there, proving that probability of A equals probability of B, there's a couple ways that you can do it. I mean, the way I have in my solutions, you can use the fact like probability of A intersect B is less than or equal to probability of A, and less than or equal to probability of B. So if so then you can use those inequalities to get you probability A greater than or B, probability B greater than A, which of course implies they're equal. The most common mistake on this one was that a significant number of people wanted to say that since like probability of A union B equals the probability of A intersect B, then those individual sets must also be equal. That is not a true statement, but like, well, a simple example of that, if you have a continuous outcome space, say like a uniform distribution on 0 to 1, for instance, then like the probability of the open interval, or of the closed interval from 0 to 1 is the same as the probability of the open interval from 0 to 1, since the probability of getting exactly 0 or 1 is 0, but those are not the same sets. So the fact that 2 sets have the same probability does not imply that the sets are equal to one another. And that was the area where probably the most common mistake on this one. So, any questions about this? Okay, final question. This was kind of another mean problem to put on the exam because we will be covering sums of random variables very shortly, but I hadn't taught that to you yet. It was, again, just trying to see if you can think out of the box a little bit, that based on things that I have taught you, you could derive the formula for this. That to find the probability that x1 is equal to m, given that x1 plus x2 is equal to n, well, just using our standard probability formulas, that's the probability that x1 equals m and x1 plus x2 equals n, divided by the probability that x1 plus x2 equals n. Now the numerator of this is fairly straightforward. That's just, in order for both of those statements to be true, you have to have x1 equal to m, x2 equal to n minus m. They're independent, so those probabilities just be the probabilities of the individual events. The denominator is a little bit trickier, that there's n different ways that x1 plus x2 could be equal to n. You could have x1 equal to 0, x2 equal to n, x1 equal to 1, x2 equal to n minus 1, so on up to x1 equals n and x2 equals 0. Since all those events are disjoint, you can get the total probability just by summing up each of those individual scenarios. So you sum up the denominator and it ends up being this ugly mess, and you combine terms and the e to the minus lambdas cancel. And not very many people did this problem, but most of the people who did it did pretty well on it. Most people made it at least this far, and if you made it at least this far, I only took off like a point or two if you didn't simplify things. But to fully simplify this and get all of the points, the trick was to notice that the denominator of this thing, after canceling out all the e to the minus lambda terms, by the binomial theorem, that's just lambda 1 plus lambda 2 to the nth power, and the top reduces to n choose m times lambda 1 to the m, lambda 2 to the n minus m, which you can write like this as n choose m times lambda 1 over lambda 1 plus lambda 2 to the n times lambda 2 over lambda 1 plus lambda 2 to the n minus n. If you want to notice something kind of cool, that note the lambda 2 over lambda 1 plus lambda 2 is just 1 minus lambda 1 over lambda 1 plus lambda 2. So if you're looking at this closely, you'll see this is actually the PMF of the binomial distribution. So we just proved that the distribution of a Poisson given the sum of two Poissons is binomial. So, yeah. So that's the last question on the exam. Any more questions about any of this? Like I said, if anybody didn't understand any of this, feel free to shoot me an email, come talk to me, whatever the case may be. I mean, similar stuff could potentially show up on the final or a qualifying exam, so try to understand this. I'll try to be a nice person and not put question 6 on the quals, but so let me stop